So today we will consider one more class of polyfunctional compounds, lipids. And the second part will be devoted, the second part of the lecture will be devoted to colloidal systems. Again, because lipids belong to surfactants. And I'll say a few words about colloidal particles that can be formed from such compounds. Lipids. This definition is from of course, it says nothing about the structure and functional groups of lipids. Because, for example, mineral oil or petroleum, it's naturally occurring, well, not compound, of course, it's a mixture, but it's insoluble in water and soluble in nonpolar organic solvents, but these compounds are not lipids. As lipids are polyfunctional compounds, the classification is, I would say, a little bit confusing. And first of all, the first variant of classification depends on their ability to be hydrolyzed or not. Hydrolyzable lipids contain usually ester functional groups or amides. Non-hydrolyzable lipids are hydrocarbons. We won't discuss non-hydrolyzable lipids at all. I'll just, well, to show the structures of some non-hydrolyzable lipids. By the way, hormones belong to non-hydrolyzable lipids, but this is the problem of biochemistry. We won't consider them at all. And hydrolyzable lipids can be classified as simple lipids and compound lipids. Simple lipids are waxes and fats and oils. Well, probably wax is the simplest variant of hydrolyzable lipid. It's just an ester of long chain of fatty acid. Fatty acids are organic acids that contain a long hydrocarbon chain and long chain alcohol. So it will look like this. For example, can you see the screen? Sorry, I'm worrying each time.
Yes. I can.
Okay.
Yes.
For example, you have carboxylic acid, stearic acid. I'll show the formulas a little bit later. COOH and, well, any alcohol with a long chain, let it be C16, for example. H, if it is saturated, the formula is 2N plus 1, then it will be 33. And to draw the formula of such simple lipid, you have to remove, it will be just an ester, remove OH from an acid, hydrogen from alcohol, and 17H35 COO 16H33 plus water. Well, it's of course just a scheme of ester formation, but the reaction is well known, I hope. And this is the functional group of this simple hydrolyzable lipid. The other type of simple lipid is fats and oils. The base of such lipids is glycerol, triatomic alcohol. And again, if you esterify glycerol with carboxylic acid, I'll write just R here as a symbol of hydrocarbon chain. Again, OH from acid hydrogen from an alcohol. To esterify all OH groups, we need 3 molecules of an acid, and the result O, this oxygen belongs to glycerol R. O, C, double bond O, R. So again, we got an ester, a hydrolyzable, simple hydrolyzable lipid with 3 ester functional groups minus 3 molecules of water. If this hydrocarbon chain is unsaturated, you will get liquid esters, and they are called oils. If saturated or mainly saturated, the result will be the formation of solid compound that it is called fat. But compound lipids, besides alcohols and residues of fatty acids, can contain the residues of phosphoric acid, sugars, amino alcohols such as cholamine, choline, and amino acids. In serine, there is carboxylic group, but it can be considered as amino alcohol because besides carboxylic group, it contains OH and an amine group. But it doesn't matter whether it is simple lipid or compound lipid, both will contain the residues of fatty acids. And fatty acids are carboxylic acids with long that contain 4 or more, but well, usually they contain in compounds you will consider, they will contain more than 4 carbon atoms, and they have some specific properties, and these are, first of all, unbranched carbon chain. Then they contain even number of carbon atoms, and including carbon in carboxylic group. This is explainable because the synthesis of such fatty acids is the process of ester condensation, such as, for example, condensation of acetyl coenzyme A. And each step of ester condensation will add 2 carbons in this carbon chain. That's why the result is even number of carbon atoms. In unsaturated acids, double bonds have cis configuration, and I'll tell about it a little bit later why. And but these double bonds will be separated by one CH2 group. So there is no conjugation in unsaturated fatty acids. So these are fatty acids. Well, you are supposed to memorize the first two, palmitic and stearic, that are saturated, no double bonds here. And if you count the number of carbons, it will be 16 in palmitic acid. That's why in the tail of palmitic acid, there are 15 carbons and one more in carboxylic group. As a result, 16. Stearic acid, uh, saturated, 17 carbons in the tail and one more in carboxylic group. Four unsaturated, alleic, linoleic, and linolenic. Each time you add one more double bond, and as you can see, in all compounds, this uh, double bond has cis configurations. CH2 is one side with respect to the plane of pi bond. Non-conjugated system. No conjugation here because carbons between two double bonds have sp3 hybridization. The structure of alleic, linoleic, and linolenic acids is similar. COOH group, and the first double bond will be between the 9th and 10th carbon. It means that here between the 9th carbon and carbon in carboxylic group, there are 7 CH2 groups. While in arachidonic, only 3, as you can see, and it has 4 pi bonds in its structure. Two essential fatty acids, linoleic and linolenic, must be obtained from food because we cannot synthesize it. And this is the example of the other type of nomenclature of fatty acids. By the way, all of them have trivial names. That's because they were isolated from naturally occurring compounds and got their trivial names. I mean, all of them. In case of unsaturated acids, trans isomers that are not components of naturally occurring lipids usually don't have trivial names and should be named using substitutive nomenclature. So this is the other type of nomenclature for unsaturated acid. Probably you have heard such expressions, unsaturated omega-3 or omega-6 carboxylic acids. You have to count the position of the first double bond, not from carboxylic group, but from the end of this long chain of fatty acid. So the last carbon atom is considered to be omega-1. That's why linolenic is omega-3 unsaturated acid. 1, 2, 3. The first double bond is in the third position from the terminal carbon. Alleic acid is omega-9. There are such questions in your online test, so please be attentive. The other type of classification of lipids is based on the nature of alcohol that is esterified by fatty acids. If this alcohol is glycerol, the result of esterification will be the formation of glycerolipids. If it is sphingosine, I'll show it later, it will be sphingolipids. So glycerolipids can be simple lipids or compound lipids. That's why classification is confusing. And this classification does not include waxes, because in this classification, simple lipids are triglycerides only. And these are fats. I told about it. If triglyceride contains saturated residues of fatty acid or oils, if they are unsaturated. But besides the triglyceride, glycerolipids includes some more subclasses, and these are phosphoglycerides. This is the general formula of complex lipid based on glycerol. In all these types of lipids, the first and the second OH group are esterified by the residues of fatty acids. They are blue here. And X here can be the residue of phosphoric acid. Then it will be phosphatidic acid. If we add amino alcohol to phosphatidic acid, we will get three more subclasses of phosphoglycerides, and these are serencephalines, cholinecephalines, and lecithin. Let's draw all these formulas. Two more words about the structure, the spatial structure of glycerolipids. In initial glycerol, there are no chiral centers at all, because this carbon, the central carbon in the molecule of glycerol, has two equivalent substituents, CH2OH groups. But you esterify OH groups with the residues of, well, any. It can be fatty acids or phosphoric acid, any. It becomes chiral. So, because this carbon in the center of the molecule of glycerol becomes chiral, it has four different substituents now. All our lipids, processes of metabolism, all of them are L-glycerolipids. But I will draw the formulas of lipids as if they don't have spatial isomers. Just the scheme of formation. So it was triglyceride. Let's take glycerol again. Add two molecules of, let's take different fatty acids. Let it be oleic and stearic, just as an example. And phosphoric acid. Now let's remove water. OH goes away from an acid and doesn't matter whether it is organic or not. And again, it's not a real reaction. It's just a scheme of lipid formation. One, two, three, four, five. OH and OH. Oh, voila. We got phosphatidic acid that contains the residue of oleic and stearic acid. Functional groups in this glycerolipid complex lipid, three ester bonds, OC double bond O and OPO, like in molecules of nucleotides, because the reaction, even formal reaction between an alcohol and an acid, leads to formation of an ester. So this is an ester bond. And now let's add any amino alcohol. It can be monoethanol amine or cholamine, or choline, as completely methylated cholamine, or serine. We are not interested in amine group in serine, neither amine group nor carboxylic. Only the presence of OH here is interesting because I'm going to form a new ester between phosphatidic acid and any of these amino alcohols. OH from acid, hydrogen from an alcohol. I won't draw the formulas of all possible phospholipids. Oh, sorry, P, O, O, H, O, CH2, CH2, NH2. So this is phosphatidylcholamine. Oh, I forgot one more tail. Functional groups here are ester bonds or ester functional groups. And in the residue of phosphoric acid here, there are two ester bonds. So the answer to the question, how many functional groups? 1, 2, 3, 4 ester functional groups. pH of our blood is 7.35 plus minus 0.05. And as you can see here, we have OH group, acidic center, and NH2 group, which is the center of basicity. That's why such type of phospholipids, they exist in the form of internal salts in which hydrogen from OH center of acidity goes to the center of basicity, and NH2 group turns into NH3 with plus, and minus will be on oxygen. But if you draw the formula of lipid in the first variant without any charges, it won't be a mistake because we just were writing the scheme of formation of such lipids. You can take any of these amino alcohols. The idea will be the same absolutely, hydrogen from OH and OH group from the residue of phosphoric acid. That's why you have the same table in your workbook. I'll show it right now before discussing the structure of sphingolipids. Here it is. I suppose, well, it's the best table that helps to understand and to memorize the structures of different possible types of glycerolipids. So the first and the second OH in glycerolipids are esterified by the residue of fatty acids always. If the last one is esterified by fatty acid, it's a fat or an oil. If phosphoric acid, we did it phosphatidic acid, and this is our phosphatidylcholamine. Here in the form of internal salt, as I did it. It can be phosphatidylcholine, the scheme of formation will be the same, or phosphatidylserine, does not matter. But all glycerolipids are esters, and this is the main feature of glycerolipids. Now sphingolipids. First of all, instead of glycerol, the alcohol in sphingolipids is sphingosine. Sphingosine is unsaturated amino alcohol with two chiral centers. And the residue of fatty acid is attached to amine group. So the difference between glycerolipids and sphingolipids is the following. Glycerolipids are esters, but sphingolipids are amides. The first OH group, or, well, probably the third, is always free in sphingolipids. But the last one can be free or can contain some substituents. Now let's draw a few formulas of sphingolipids. I won't draw the total formula of sphingosine itself, just the part I'm interested in. I like to draw it like this because it resembles the formula of glycerol. But as it has two chiral centers, of course, it has special configuration. So let's add a fatty acid, alleic. Hydrogen from NH2 or H from carboxylic acid. This OH is always free, non-substituted. This type of sphingolipids is called ceramide. And this is the functional group of ceramide. And this is an amide bond. To this OH, the first one, we can add phosphatidic acid and then the residue of choline, or it can be sugar. If it is sugar, it can be any hexose, galactose, mannose, or glucose. If so, it should be in the form of beta-D pyranose. This is the scheme of formation of such lipids. I'll remove water like this. Look, the residue of my sugar has beta configuration. Let's have a look at our table with classes of sphingolipids. So this is an amide bond, and this is R, this is the tail of fatty acid. In case of free OH group at the first position in sphingosine, the class is called ceramide. If we add phosphoric acid, again removing water, and after that a molecule of choline, again removing water, hydrogen from choline, OH from phosphoric acid, it will be sphingomyelin. If it is the residue of sugar, it will be cerebroside. And as here, the residue, this is the residue of galactose. So this is galactocerebroside. It must have better configuration here. Chemical properties of lipids are quite simple. First of all, this is the peroxide oxidation. I hope you remember that peroxide oxidation leads to formation of peroxides. This is the mechanism of peroxide oxidation, just to remind you. And if it is this long unsaturated chain, then a particle, a free radical that will initiate the reaction of peroxide oxidation will attack carbon atom next to double bond. This is, well, it can be a part of alleic or linoleic or linolenic acid, because in each of them the first double bond is between the 9th and 10th carbons. So this X can attack both carbons. The result is the formation of allyl free radicals. Each will exist in two forms, and each of them can react with oxygen, forming hydroperoxide. What else? It can be the reaction of hydrolysis, because either glycerolipids or sphingolipids belong to hydrolyzable lipids. It can be the reaction of hydrogenation. In case of presence of unsaturated acids in a given lipid, or bromination, for example. Well, let's write the reaction of hydrolysis just as an example. Let it be our phosphatidylcholine. To hydrolyze an ester bond, we need a catalyst, and it can be an acid. So we can do it in acidic medium or in the presence of a base. In the presence, the hydrolysis in the presence of a base is called saponification. This is phosphatidylcholine. So how many covalent bonds do we have that we can hydrolyze? 1, 2, 3, and 4. Here, 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 and here. Because these oxygens, they belong to initial alcohols. So 4 molecules of water, and in the presence of an acid, we will get glycerol. And fatty acids. You just formally add water to each ester bond, hydrogen to oxygen or H to carbon, plus alleic acid, plus phosphoric, and plus cholamine. If it is the hydrolysis in the presence of a base, the only difference will be the formation of salts for compounds that can react with base. Alcohols cannot. So the product will be glycerol. Instead of carboxylic acids, we will get their sodium salts, sodium or potassium. That's why the hydrolysis in the presence of a base is called saponification, because sodium and potassium salts or fatty acids are called soaps. Instead of phosphoric acid, we will get phosphate. And, oh, sorry, it's NH2 here. Of course, it's cholamine. Cholamine will stay as it is because neither NH2 nor OH can react with sodium hydroxide. Of course, we have to balance the reaction. So it's not difficult, not a problem to draw, to write the reaction of hydrolysis. Just bear in mind that in case of compounds that can react with a base, they will form corresponding salts. I hope you will be able to write the reaction of hydrogenation and bromination yourself. It's just the addition of hydrogen to double bond. Instead of C17H33, the reaction of hydrogenation will produce saturated acid, H35. In case of bromination, will be addition of bromine to double bond. Now, I want you to record some. Oh, I didn't show. Lipids are components of cell membrane. And this is a part of, drawn schematically, a part of our cell membrane, not our, hydrophobic, non-polar hydrocarbon tails of all fatty acids are directed inside the cell membrane. And they are hydrophilic polar functional groups. This is, as you can see, phosphatidylserine. I suppose these are residues of glycerol. It's phosphoric acid, the residue of serine. So this part is polar part. It contains oxygen atoms and phosphorus atoms and nitrogen atoms. So this part is polar. And as like dissolved like, polar functional groups are directed toward water, polar solvent, and non-polar tail inside the cell membrane. And the interaction between them forms here non-polar part, non-polar zone of cell membrane. Probably you know that cis isomers of 80 compounds have a lower melting point than trans and saturated compounds. That's because in case of cis isomers, they cannot be packed in the crystal tightly, and it decreases the melting point of a compound. If you compare the melting points of these two glycerolipids, tristearine, it contains three residues of stearic acid, and it's saturated and straight and can be tightly packed in the crystal. And triolein with the residues of alleic acid. This kink does not allow this tail to be packed tightly. That's why such uh, lipids, first of all, will be liquid, and it will be oil, and this one will be fat. And it's important uh, for living organisms because the presence, the higher the amount of unsaturated fatty acid in cell membranes, the lower will be their melting point. That's why seafood, uh, is rich of unsaturated omega unsaturated fatty acids because uh, it decreases the melting point of cell membrane and allows it to stay liquid uh, even under low temperature. I have read about a kind of fish that managed um, manages to change the content of unsaturated acid in its organism. In summer, when the temperature is high, the content of unsaturated acid mm, decreases, but in winter, when temperature is lower, the content of unsaturated acid increases in its organism. So, uh, lipids lipids belong to surfactants, and uh, as you, I hope you remember that surfactants are compounds that are able to decrease the surface tension on the boundary surface uh, in colloidal systems. Colloidal systems are heterogeneous systems that contains of particles of disperse phase and continuous phase, and there is a boundary surface between them. The surface tension depends on chemical nature of both phases. Uh, then temperature, the higher the temperature, the lower the value of surface tension, and the presence of solute. Surface inactive compound doesn't change, do not change the value of surface tension or increase it a little bit under high concentrations, but surface active compound or surfactants decrease uh, the surface tension on the boundary surface. How? They concentrate on the boundary surface, directing their nonpolar tails into nonpolar phase. Here it's air, and leaving their polar heads in polar solvent. In our case, it's water. Uh, and as the surface tension of surfactants is lower than the surface tension of water, the surface tension on the boundary surface begins to decrease, and when all area, the surface area, will be occupied by molecules of surfactants, the value of surface tension will reach the constant value, and it will be the surface tension of surfactant. Now let's have a look of possible variants of surfactants. It can be anionic. The polar group in this compound is, of course, this one without any sodium, because in water it will dissociate, forming sodium cations and anionic an anion, in which polar head will be this one. Cationic. It shouldn't be, it's even not, well, I suppose it should be pyridine. Well, probably the author forgot to add one double bond here. I stole this picture from the internet. There is one more mistake here. Um, Cationic surfactant. It will dissociate, forming bromine anion and surfactant itself, this particle with polar functional group and non-polar tail. And look, zwitterionic surfactant. I hope you recognize lipid. There is a mistake here, the absence of oxygen here, because it should be the residue of glycerol here. And there is oxygen between atom of phosphorus, the residue of phosphoric acid, and the residue of glycerol. But nevertheless, it shows, even with this mistake, it shows the structure of lipids, that it shows that it contains this polar functional group and two non-polar or hydrophobic or lyophilic, all variants are acceptable, tails. If this non-polar tail is rather short, a compound surfactant will go on boundary surface, of course decreasing a little bit the surface tension. If it is too long, the compound can be insoluble, absolutely. But if the length of this non-polar tail is somewhere between 10 and 20 carbon atoms, such compounds will be able to form micelles, and they are called colloidal surfactants because they are able to form colloidal particles. Uh, the concentration at which these micelles begin to form is called critical micelle concentration. When the concentration of colloidal surfactant is very low, there are only a few molecules on the boundary surface. Of course, the surface tension will stay as it is. For example, it's water. The presence of two molecules on the boundary surface won't change the value. The increasing in concentration will decrease the surface tension because the boundary surface will be occupied by these molecules, and their properties, their surface tension of this compound will determine the surface tension on the boundary surface. And at critical micelle concentration, if we still increase the concentration of surfactant in our solution, look, this surface area is covered, is occupied completely by the molecules of surfactants. They will go inside the phase, but they have non-polar tails and polar heads, and they will try to hide these non-polar tails from non-polar tails, so phase. So they will form these spherical micelles. Uh, I would like to compare the structure of Zoll, if you still remember what it is, uh, and the structure of this micelle that is formed by colloidal surfactant. In Zoll, this inner part is microcrystal of insoluble inorganic compound. Uh, I hope you remember that to stabilize such system, and the system is thermodynamically unstable due to excess of energy on the boundary surface, because the energy is equal to the product of surface tension and boundary surface. So to stabilize it, we needed to take one of electrolytes in excess. Uh, Evidently, it was the reaction between soluble salt of silver and potassium iodide. And this potassium iodide was taken in excess. Iodide anions here is potential determining ions. E is electrothermodynamic potential. This surface absorbed some amount of counter ions. Zeta potential is still negative. The values of both potentials are the same. And the first layer of counter ions is the dense layer, and this is a diffuse layer. The total structure is called micelle. Uh, Micelle without diffuse layer is granule, and core is microcrystal with potential determining ion. Now let's compare the structure of spherical micelle with uh, this inorganic micelle. So this is the core, of course. The only difference is here it is insoluble inorganic salt, and here this is an aggregate of nonpolar tails of a surfactant. These are, I suppose, carboxylic groups because uh, we have sodium salt here. Of course, these are COO minus functional group. In case of inorganic micelle, we had to add an excess of electrolyte to stabilize the system. Here we don't need it because these nonpolar tails are attached, it's just a covalent bond between carboxylic group and nonpolar tail. So this layer of potential determining ions is formed automatically as soon as these nonpolar tails uh, will combine, forming the inner part of micelle. It will be surrounded by dense layer of potassium cations, and it will be granule. And after that, the rest sodium cations will form a diffuse layer, and it will be a micelle. Exactly the same structure, and as a result, exactly the same factors of stability. But the only difference is micelles of colloidal surfactants form spontaneously because mm, they are thermodynamically stable. Uh, if you this is spherical micelle we discussed. But if you continue to increase the concentration of a colloidal surfactant in the solution, there will be too many spherical micelles and they will interact with each other, forming such cylindrical structures and after that bilayers. Uh, such uh, structures and colloidal surfactants are widely used in scientific research that because it's a model of cell membrane and colloidal surfactants are used in uh, in the research devoted to properties of cell membrane. These are uh, structures of these micelles in polar solvent, in aqueous solution, because polar functional groups are directed to polar solvent. In case of non-polar uh, solvent, you will get the reverse micelle. Polar functional groups will be hidden from non-polar solvent, and non-polar tails will be directed outward. As in normal micelle, the inner part is non-polar. In the reverse micelle, the inner part is polar. Such particles are able to absorb compounds with the same properties. I mean, normal micelle can absorb non-polar compounds, and this incorporation of these non-polar compounds in non-polar inner part of micelles is called solubilization. Solubilization. The reverse micelle will be able to absorb polar compounds inside their micelles. And in the presence of corresponding micelles, for example, the solubility of compounds in polar solvents will increase because they will be solubilized inside such micelles. Now, two more types of microheterogeneous systems. These are emulsions and foams. Emulsions and foams belong to microheterogeneous systems, colloidal particles to ultramicro heterogeneous systems. The only difference is the size of such particles, because the factors of stability will be the same, as you will see later, a little bit later. So emulsions. Emulsions contain is a system that consists of two immiscible liquids. One of them will be dispersed as droplets, and it will be dispersed phase. And the other liquid will be continuous phase, in which these droplets will be evenly distributed. Of course, such system will be unstable because the energy on the boundary surface is the product of surface tension and surface area. So to form a stable emulsion, we need something to stabilize it. To stabilize it. The emulsions can be two types of emulsions exist. The first is called oil in water emulsion, in which the disperse phase is oil, droplets of oil, and continuous phase is water. The reverse emulsion, or water in oil, droplets of water and continuous phase here is oil. It shouldn't be oil, it's just a symbol of non-polar liquid. And as you can see, there is something here around these droplets. Because without this stabilizing reagent, the system will be unstable and will decompose immediately, forming two layers. These are molecules of surfactants. And in case of direct emulsion or oil in water emulsion, a molecule of surfactants will put their non-polar tails inside non-polar droplets, leaving polar functional groups in polar solvent. In case of reverse emulsion, droplets of water will be surrounded by molecules of surfactants, but they will put their polar parts into molecules of droplets, water, water, leaving non-polar tails in non-polar phase. The type of emulsion that will form does not depend on the amount of both liquids. Only the nature of this stabilizing reagent or emulsifier will determine the type of future emulsion. In case of lyophilic or water-like, in case of lyophilic surfactant, you will get oil in water emulsion. In case of lyophobic, you will get water in oil emulsion. This property to be lyophilic or lyophobic emulsifying reagent is characterized by hydrophilic lipophilic balance or HLB balance. It's just a digit that compare the ratio of lyophilic and lyophobic functional groups in a molecule of a surfactant. It's an empirical value. But value of 0 shows that this emulsifying reagent is lipophilic or hydrophobic. It's the same and will stabilize the reverse emulsion. The value close to 20, such as for sodium salt of oleic acid, soaps, such molecules will be hydrophilic and will stabilize the direct emulsion. Because if you mix equal amount of polar and non-polar immiscible liquid and will add, for example, hydrophilic emulsifier and will shake the mixture, at first you will get droplets of water and oil, and molecules of soap will be somewhere between them. But if a surfactant is hydrophilic. Hydrophilic. It will penetrate into into droplets of water, but won't be able to penetrate inside droplets of oil. As a result, when you stop shaking the system, droplets of water will form continuous phase and you will get a direct emulsion. That's why the type of emulsion depends on the properties of stabilizer only. Uh, Emulsions can undergo the so-called inversion, because if the type of an emulsion depends on the type of stabilizer, if you turn somehow hydrophilic stabilizer into hydrophobic, you will change automatically the type of emulsion. And how it can be done. For example, you have my favorite sodium salt oleic acid. This is hydrophilic surfactant, and it will stabilize the direct emulsion. What will happen if we add to this compound calcium salt? Let it be calcium chloride. Sodium and potassium salts of fatty acids are soluble, but calcium or magnesium salts, they are insoluble. So the result, it was hydrophilic, but became hydrophobic. We changed the type of stabilizer, and direct emulsion will turn into the reverse emulsion. This process is called phase inversion. And the last type, not the last, because aerosols belong to microheterogeneous systems, but we won't discuss aerosols right now, maybe during seminar. The last type of microheterogeneous systems is foam. It can be solid foam or liquid. This is the example of solid foam, and evidently we don't need any stabilizer to stabilize such structure. But for liquid foam, it will be stable in the presence of a stabilizer only, because when you taking a shower, for example, what do you need to get a stable foam? You need a soap. This is schematically a foam without any stabilizer. Here is air and here water. The energy on the boundary surface is the product of surface tension and surface area. As the surface area here is, well, you can count. Of course, such system won't be stable. What will happen if we add a soap, a sodium salt? Let's take again a lake sodium oleic. It will dissociate, forming C17H33COO minus plus potassium cations, and it will be non-polar tail C17H33 and polar functional group with negative charge. Of course, this surfactant will direct its non-polar tail into non-polar phase and will leave its polar functional groups in polar solvent. First of all, it will decrease the surface tension on the boundary surface. And due to the repulsion between these potential determining ions, and these are potential determining ions, the system will be, well, stable more or less. The factors of stability of foams is absolutely the same as the factor of stability for ultra-microheterogeneous systems. I mean zoles and colloidal micelles of colloidal surfactants. Thermodynamic potential, of course, it will be surrounded by two layers of counter ions, dense layer and diffuse layer, because we need to do something with sodium cations. And the difference between emulsions, for example, is the aggregate state of compounds in foams. In case of emulsions, these are liquids. In case of foams, this is gas, and that's all. The factors of stability will be the same. This is the picture that illustrates the thing I was talking about. Blue area, this is water. And hydrophilic functional groups are directed to water. Hydrophobic ends are directed towards non-polar phase. That's how the presence of a surfactant will stabilize the foam. Foam stability or foam half-life. There are such questions in your online test. Is the time that is required to decrease the original volume 2 times. And one more parameter that characterizes the foam is the foam multiplicity. It's a ratio of volume of a foam over the volume of liquid from which you got the given volume of a foam. Well, that's all. Thank you. Copy the link, please. The lecture is downloaded. If you still didn't do it right now. And, well, the lecture is over.